Streaming countrywide on Prime Media Plus
on DSTV channel 885
and across the city
on 567 AM.
Welcome back. It is 9:36 exactly. Views and News through till 12 with me, Clarence. And that big appointment with the Naked Scientist is now on through till 10 o'clock. Welcome to Dr. Chris Smith, lecturer at the University of Cambridge. It is Friday and a sunny one in Cape Town. It's good to have you back.
And a sunny one here in Cambridge too. Morning, Clarence. Interesting story to kick us off with this week, because I interviewed someone with the amazing nominative determinism going on. His name's Brendan Byrne, and he studied the wildfires in Canada. It's a big paper in the journal Nature this week, because they were asking what a lot of people are asking, which is when you have a huge, great inferno like this, the 2023 Canadian wildfires were absolutely huge, even by huge fire standards. How much CO2 did that big fire produce? And their calculation puts it somewhere in the region of 600 million tonnes of CO2. And to put that into perspective, if that forest fire was a country, it would be in the top 10 emitters of CO2 in the world. And it would be a country emitting in fourth place CO2 from fossil fuel burning, if it was burning coal and oil, for example, to achieve that sort of output. So in other words, it was an absolutely massive release of CO2. And they make a couple of points. One, it produces a lot of CO2, which is not good for our carbon footprint. But it also means we need to rethink how we balance the CO2 budget sheet in terms of the perceived mitigation from forests, because we plant trees because they soak up CO2. But as long as they keep growing and regrowing if they get burned down, that's fine. Unfortunately, climate change means that they might not be relied on to regrow at the same rate as they did before. So this is a wake-up call in terms of how much CO2 comes off of a big inferno like this, but the fact that we can't take trees for granted as a sponge to soak up our CO2 in the future. So therefore, we really do have to bear down on our emissions more carefully.
Sure, and it renders our mitigation efforts null and void, does it not? Such a huge fire.
Well, the point that Brendan made to me, because I said to him, well, where does this leave us? Because if we rely on trees to work as sort of CO2 sponges, are we back to square one? And he said, well, forests do regrow, but the data they have shows that compared with the previous 44 years, this was an unprecedented year, this 2023 season, of very, very extremely high temperatures, but also extreme drought. And it meant that tree growth was much, much lower as well. So if you were to extrapolate that into the future, we will see less tree growth, less rate of growth of green plants, therefore less CO2 drawdown. So if we burn the stuff off but then don't replace the things that locked it up to start with, it will translate into a net rise in CO2 that previously we thought had been locked away for a while. So that does need taking into account and is a big concern.
Okay, well, the Naked Scientist is here to answer your question. So let's go to one of those voice notes, Joe. Let's take it.
Good morning, Dr. Chris, and good morning, Clarence. It's so nice to be able to listen to you guys again. 1 month ago, I was involved in a motorbike accident and haven't been able to keep up with the show since then. So my question is, in the accident, I broke my femur in 3 places and my arm as well. They put it all back together with a long pin and screwed everything up. My question is, how do the bones repair themselves? How do they start to join everything with the pins just holding everything in place? But I'm amazed at how the bones can actually rejoin after a clean break. Thanks, guys. Keep well.
Great question. Sorry to hear about the accident, and I'm glad you're on the mend, and it's really good to have you back with us. In terms of how bones develop and repair themselves, they're continuously being remodeled. If you look at the structure of a bone down the microscope, you can see that it is not solid like a lump of rock. It is full of tiny holes and pits, which are called Haversian systems, with blood flowing through them. And in concentric circles around those holes and pits are cells. And the cells come in 2 flavours. They're osteoblasts, which make bone, and osteoclasts that eat bone. And these cells are in what we call a dynamic equilibrium. So the rate of building is roughly the same rate as eating. So your bone stays roughly the same density during youthful health, and you continuously rebuild it. Now, if you break it, because there's that rich blood supply, the first thing that happens when you bust a bone is that bleeding happens into the site. As long as the bone isn't massively displaced and there is contact between the bone ends, and that matters for getting obviously a good anatomical healing, then the cells that I just mentioned, the osteoblasts and the osteoclasts, will migrate out of the broken bone ends and into the blood clot that forms at the site of the trauma, and they will begin to lay down fresh bone in the case of the osteoblasts, and then the osteoclasts will come along and eat away the fresh bone which is making a mess because it's just chaotic and laid down in a haphazard way to start with to heal the fracture, and it slowly remodels and rebuilds it back into the right structure and shape of the bone, almost as good as perfectly what it was to start with. It's a bit like if you cut your skin will grow new skin cells that move into the cut site, into the blood clot, and lay down new skin, and it heals with an almost perfect replica. There may be a little bit of scarring, so where there's been a fracture in a bone, a radiologist would see that on an X-ray, but the bone will re-knit itself together, and then you'll spend the next X number of years of your life remodelling that bone. Now, why you have to put screws and pins in is, that I mentioned earlier, if the fracture is such that it is more complicated and the ends don't meet, A, it's unstable, B, it's unsightly and might be deformed and anatomically not so useful, and C, it's not going to heal up well. So they use various measures, including long pins and screws, to bring the bits together so that, united by the force of those pins pulling them together and the blood clot that's in there, good blood supply can be restored and the bone can then reform in that blood clot and then remodel over time. So bone is a dynamic thing, and for most of our healthy life, we are continuously eating our bone and remaking our bone across our lifetimes.
Indeed, and forward to a speedy recovery. Thank you for that question. Abdul is very upset about the fact that weeds grow faster than his plants. Why do they grow faster than my plants?
Well, weeds, of course, are plants. They're all plants. They're all part of the world's rich natural tapestry. We've just selected plants that we want to grow because we like them, and the weeds are in competition with them. And there are some plants we do like to grow that do grow so well that, in fact, we've discovered that they're less good for the environment, and we call them an invasive species now. There are things like rhododendrons, for example, that we've moved to the UK, which are a big problem. There are things like Japanese knotweed, which was, again, brought to countries like the UK and have become invasive species. People are growing a lot of bamboo in the UK as well, for example, to act as natural breaks and barriers in their gardens, and then they've discovered that these things are quite hard to control. They've become an invasive species. So the definition, what's a plant we want and what's a weed, is a fluid thing anyway, but generally plants are all part of life's rich tapestry. The same mechanisms have selected them to fit into their environment the way that best suits them and best suits the environment. But if you try and force nature's hand by growing only a selection of things, then you leave open the opportunity for other things to try and move in. And those other things might be a better fit with that particular environment than the plant you want to grow, which means your plant is at a disadvantage compared to the weed that wants to grow there because it's better adapted to that environment. So really, the reason that it's hard to garden is because you are continuously fighting nature and disorder, because nature is moving towards disorder and diversity. And when we garden, we tend to choose a monoculture or a much more limited repertoire of things we want to grow in an environment that might not be best suited or natural for that plant. So it's always working at a bit of a disadvantage.
Chris Smith, Dr. Chris Smith, why do some people or animals float and others sink when they drown? That comes from Keith, the Blue Bull.
Hello, Keith. Well, the answer is that anything floats because it's less dense than the thing it's floating in. Most commonly, that means water. So to float, you've got to put something into the water which has a density. In other words, the mass of the object, is, when divided by its volume, is lower than that of water. And the density of water is 1 gram per centimetre cubed. The density of the average human is around about that, which is why if you just drop us in the swimming pool, we will float. But if you drop a brick in the swimming pool, it will sink, because the amount of water that you're pushing out of the way, that's your volume. If you push out of the way with your volume a bigger weight of water than the thing weighs itself, then the buoyancy force, the upthrust, will be greater than the gravitational force trying to pull the thing down, so it floats. So different people come in different shapes and sizes and different densities. And therefore, if you have the right body makeup, that means your density is lower than water, then you will float better. If your density lots of bones and muscles, which weigh a lot and a high density, you're going to be more likely to sink to the bottom like a stone. And this is why you will find that some people with some body shapes make better swimmers and tend to be better represented in the Olympics than people from other parts of the world.
Okay, Anne is in a state. Anne from Thornton is going to tell you why directly. She's on the line. Welcome, Anne.
Good morning, Dr. Smith. I had my duck eat my spinach plants, but there were so many other plants, like spigworm, which is a fat leaf, and lots of other plants, and it just walks past the others. So why do ducks, I'll just concentrate on the ducks, why do they eat some plants and not others? How do they know what the difference is?
Well, in the same way that teenagers, toddlers, and even grown-ups like eating certain things and they detest the taste of other things, it's all down to choice and what we like. And what we like tends to be determined by A, what we grew up with and saw other people eating, and B, what we genetically are programmed to like or dislike. And ducks are no different. So they are social species. They watch what other animals eat. And you've probably seen the news stories about seagulls stealing people's chips at the seaside. Seagulls will tend to steal food that they see other animals eating because that gives them a pointer that it's safe. So your ducks might have seen other ducks eating the spinach, and that might have led them to think, well, that's safe for me, I'll eat that. But also there may well be things in the spinach that make it more attractive and palatable to a duck. Spinach is rich in iron, it's rich in B vitamins and folic acid, and all these things a healthy body needs. So I suspect just as you're growing the spinach because you like it, the ducks have learned that they like it too, and it's also safe, it doesn't make them ill, so therefore they're getting a win-win.
Thank you, Anne, for that question. Vincent is in Muizenberg. He's on the line as well. So he jumps the queue with his question about evolution. Go ahead, Vincent.
Thank you, Dr. Smith. If we have all evolved from a small group of ancestors, why do we have different blood types?
Hi. Well, the answer is that we have evolved from a smallish group, but we've evolved for a long time. And as we've diversified, you will get more and more variation in a population. We only have Group A, Group B, Group O, which is neither A nor B, and Group AB, but some animals have 7. The cows and sheep and things have 7, 8 blood groups. Dogs have about 5 blood groups. So we're not unusual in having multiple blood groups, and there are 8.5 billion people on Earth. That's a lot of rolling of the genetic dice in the about 6 million years that humans have existed since, or our ancestors have existed since we split away from, say, chimpanzees. So we've had plenty of time biologically to evolve genetic variation and differences between us, and that ends up settling on the 4 main blood markers that we've got. There are lots of other blood groups actually, but they're represented at such low levels genetically that we don't tend to regard them as important from a blood transfusion perspective. We look at the 4 main blood groups because those are the ones that the major blood groups that make a big medical difference. But there are other markers, and if you look in populations around the world, you will find other people with rarer forms of hemoglobin and other markers that single them out and show how rich nature's tapestry and the diversity of human genetic diversity is across the earth.
Rebecca wants to know why her temperature goes down when she's feeling ill.
Hi, Rebecca. Well, it should be the opposite, actually, shouldn't it? Because when we are ill, if you have inflammation, and inflammation is actually a process by which you send signals from the immune system to recruit other parts of the immune system to change the way blood vessels work, to change the way the nervous system works. And those signals are all about fighting off infection, but they also travel around in the bloodstream to the hypothalamus in the brain. And the brain's hypothalamus has a region which is basically setting your internal thermostat. And it does that by making you put on clothes or take them off. It changes your metabolic rate. It changes things like shivering. It makes you go indoors rather than stay outside, etc. That is sensitive to these so-called inflammagens as well, and it should wind up your temperature if you have inflammation. If you're feeling ill for other reasons, and you're getting cold, then the likelihood is that it's probably not inflammation that's making you feel ill and something else is making you feel icky, and you should look at why or what factors tend to provoke that, because something must be making that happen, and there's probably a causative factor. Is it something you're eating? Is it because you slept badly the night before? So it may be a non-inflammatory reason you're feeling unwell, and that isn't going to be linked to temperature.
Okay, let's take a listen. Joe has got it sorted.
A question for the naked scientist. Platinum group metals, some of the platinum group metals is said to only originate from extraterrestrial sources. I was wondering, is that the same for other metals like gold, for example, as well?
Yes, the complicated metals, and in fact all the complicated elements we have on Earth, all come from the deaths of stars, which are blown up elsewhere in other systems and spewed their guts up into space. So the carbon in your body comes from a dead star. The nitrogen that's in our atmosphere comes from a dead star, as well as some other processes. The gold that you're wearing in your wedding ring comes from a neutron star smashing into another neutron star and causing a huge explosion. So yes, these substances that we have and these more exotic elements definitely all come from the deaths of, from the lives and deaths of stars out there in the wider universe, and happen to be in our cosmic neighbourhood and have coalesced when the Earth formed. The only thing that we can say we absolutely didn't get from that is hydrogen and maybe a bit of helium, because hydrogen and helium were the products of the Big Bang. That's how the universe started. So everything starts with hydrogen, and all those big complicated elements have been built up by fusion and supernova explosions since then. In the 13.8 billion years the universe has been burning hydrogen.
Let's go out with this one. It sounds like a joke, but I'll ask it anyway. Why do snails come out when it rains? Walter wanting to know, Doctor.
Hi, Walter.
Smith.
Well, the answer is, and I'll tell you actually, I was taking part the other day in a snail race. Have you ever done this, Clarence? Done a snail race?
Yeah, I've got better things to do. Thank you.
Well, no. What you do is you put your snail on the board, and then everyone bets on a snail, and you bet about how fast it'll go across and whose snail's going to get to the other side of the board first, and you lay big bucks. This is a big deal.
Is this a 2 or 3 day game?
It can be 3 weeks, but my snail wasn't doing very well. So I said to my friend, well, shall we take the shell off, because it probably weighs quite a bit and that might speed it up? And they said, no, that'll make it more sluggish.
That's the joke I was looking for.
But the reason they come out in the wet is because they are moisture-loving creatures. They thrive on moisture. They glide around on effectively a foot which is lubricated by moisture and mucus, and hot, dry surfaces will soak up their moisture very, very rapidly, dehydrate the slug or the snail, and it will kill it. So they tend to retreat into shady, cool areas and stay there until it usually gets dark, because that means fewer predators like birds, but also it's damper and cooler, so they're less likely to dry out. But when it rains, A, they might have been flushed out of their hiding place by the water, but B, they're not so at risk of being dried out by hot sunshine and dry surfaces, so they can venture out with more impunity when it's wet.
We appreciate that question, Willem, and we appreciate your time as always, Dr. Chris Smith, lecturer at the University of Cambridge, our very own naked scientist. He'll answer your questions every Friday just after 9:30. Now 9:58 with news coming your way at the top of the hour, and Natalie Malchas standing by.